in order to sum up l2v1 to all the way till here, alright, this stuff over here, this video will somewhat summarize what we have learned, hopefully to get a better understanding of the bigger picture. What let's come back to here is that for stability, it's just a measurement of state, whether is he stable or is he unstable. Alright, and we actually measure stability using stability criterion, alright, as ensuring that it doesn't encircle the -1, alright, if there's a -1 over here. So far so good. Our robustness is a measurement of the stability. Alright, it all depends on what type of measurement are you looking at, or what type of robustness are you looking at. If a person gonna push this guy, then this person is actually robust against this pushing, alright, while this not robust against this pushing to this person, alright. However, in both cases, if an N were to push this person, it is definitely robust. Likewise, if an N were to push this person, he is also definitely to be robust. So what is the condition that we are looking at? What type of things are we looking at as such that it is robust or not robust? And therefore, look at all these three things: the gain margin, phase margin, and the vector margin SM, or 1 over S. Alright, where S is 1 over 1 plus CP. Alright, gain margin is the point the point of the Nyquist plot at the real line, alright, at the real axis, relative to this -1 point. So this distance over here is actually the gain margin, alright, while this distance over here is shown over here is inverse of gain margin, meaning it is simply lambda. Alright, over here is simply 1 over lambda. Okay, while phase margin on the other hand is the angle before you reach, alright, is the point, your Nyquist plot point, where its angle before it reaches -1, alright, is this particular angle over here. So therefore, the bigger the better for this case also. So gain margin better, higher better, phase margin higher better. So vector margin also higher better. Why? It's because this is the point. You're talking about -1 to the nearest point of the Nyquist plot. Alright? And therefore this is the distance between -1 and CP. CP describes this curvature. Alright, CP is an equation that describes this curvature. That's all. So if this distance is bigger, meaning it's gonna be like that, so this means your Nyquist plot is actually further than -1, right? And therefore it is stable. And therefore this is one way to measuring robustness. Alright, it's a measurement of stability, some sort of that meaning. Alright, this measure how far away are you before you become unstable. So these are the stuff in order to determine stability, whether are you near to stability or not. We can also go a further step in terms of the vector margin to talk about the distance, where this is 1 plus CP naught. Alright, and that this distance over here must be greater than the distance here. Alright, orange to black color one, where this is L minus L naught. Okay, with a certain inequality over here. Alright, now whole thing divided by 1 plus CP naught, alright, will give you percentage of how this thing change along time with regards to its original system. Alright, this thing is original system, as you say, right? Where you just first started to implement this certain plant or this certain system. And a long time this actually they perturb and perturb and perturb. So we actually use this form of method to find the percentage, or to a certain extent the ratio between how it perturbed and its original distance or original vector margin before it actually fails, some sort of the meaning. And we can also rewrite that instead of L minus L naught, can also state that it is, instead of 1 plus CP naught, we can also state that it is actually some W1, alright, some boundary. In other words, instead of this distance over here, you can actually set it to a range, alright. Therefore, you find that this point over here is the dangerous spot. Anywhere more than that is also unstable, and therefore instead of -1, this is somewhere nearer or somewhat further than -1. So if -1 is over here, you're actually further away. So you can actually increase your bound such that your system is bounded. So once it reaches, it's considered fail. So if it further reaches to -1, definitely fail. So this is something like a safety factor or some sort. Alright, so W1 is simply a function. Alright, W1 is simply a function that could help us determine that. Alright, with regards to some equations of CP0, I would say. Alright, same thing as for 1 over S. Alright, this is in other words W2. Alright, some equations, and this particular line over here, we call this B, the bandwidth. Alright, same as this part over here, somewhat of the cutoff frequency type of saying. Alright, where at this point is always a maximum. Up till here it actually cut off and at this particular frequency, and then it drops down. Alright, at this point it's increasing, and at this cutoff frequency it increases all the way. Alright, and we also discussed that we are, as for 1 over T, alright, meaning this relates to the system of 1 over L0 and 1 over L, if you still remember. 1 over T relates to the system where it is 0 to B, which is this portion, you're considered stable. Alright, likewise for S, this over here you're considered stable. Alright, because you are constantly giving an output. Alright, you actually didn't go down to a certain extent. Do take note that this T is a low pass system, S is a high pass. Alright, if you were to compare back in just the last particular video, this graph is talking about 1 over S, and therefore this particular video is actually a low pass system. Alright, if you were to link it down, alright, a low pass system. While 1 over T is now a high pass. Alright, previously T was low pass, now 1 over T inverse is actually high pass. So please remember that. And therefore, as I say, this is a measurement of the distance between two Nyquist plot. Alright, this orange color and the black one, with regards to its original nearest unstability. Alright, meaning 1 plus CP over here. Alright, this portion over here. If I were to zoom in, 1. Alright, we are actually bounded. Anything larger than this bound, like that, this means you are unstable. And also, if you were to zoom out, if you still remember this stuff, this block diagram, we can actually dissect them and become this formula, right? Where this is the filter or the input function with the noise and the disturbance. Alright, and what is so important of T and S relationship is that we want S to be as low as possible, because you minimize the disturbance. Because if you increase, we know that T plus S is equals to 1. Alright, so if S increases, T will actually decrease. Alright, so you have more disturbance than your input reference signal, which is not very nice, right? And therefore we want S to be as low as possible, and we want T to be as high as possible, but not maximum. Because if T is maximum, this actually would cause the plant itself to become very unstable, and therefore we need to find a way to ensure that this T is maximum, alright, optimally maximum, such that the plant can still work, but it is still considered stable. Alright, and therefore this is why T plus S must be equals to 1, such that T and S are not peak. That's just the meaning of that. And if S is lower, alright, this then means that we are talking about the reference signal and the noise. Then from here, if we were to minimize the noise, then we can better present our reference signal. Alright, nonetheless, we can also keep the disturbance down while measuring the quality of the noise and to track the noise and things like that. Alright, with just a quick review, is that over here, this thing over here, L is equals to CP. Alright, C is a PID controller. Alright, just an example. Okay, such that P also has its own transfer function, we don't know, alright, but this transfer function multiplied with C will give you L0, alright, and then you can construct your T and your S, alright, based on this L0, and then you can construct the Nyquist plot and the block and the Brody diagram. And from here you see your curve is far away from -1, alright, the gain margin, the phase margin and the vector margin is all so far away, and therefore as you can see the signal is always constant, it's quite very stable, alright, and it's at the crossover. If you were to remember, this blue color one is in fact the S, while the green color one is the T. S is a high pass, T is the low pass. So when add them up together, you'll have somewhat of a filter or not filter, but rather a signal that is somewhat pretty much constant. Alright, in other words, also stable. Alright, and instead the plant itself can be further dissected into M and a P plant, where this M is actually the actuator and the plant is simply its plant itself. Alright, it's machined. Alright, same thing, CS, I mean this is the controller, PID, alright, over here, multiply by whatever equation you have over here, alright, you'll have L, alright, P is equals to MP, which is this one, so CP, alright, which is P times C, will give you L, and then you sub it in, alright, you will get something like this, okay, and as you can see, by adding this actuator, another certain form of a disturbance, you're actually shifting your Nyquist plot further up, as you can see in this side. Alright, so you're actually making your whole system become a little bit unstable, which is a little bit over here. So far so good. However, the high pass and the low pass are still the same for S and T. Alright, and as you further increases, as when the more you use this plant, alright, the system getting more and more unstable due to wear and tear, and therefore as you can see, this Nyquist plot itself actually moved, alright, to a further more instability if you were to compare. Although this is not very clearly shown over here, but as in terms of the Brody plot, as you can see, for this pipe and this pipe, this one is actually much larger, alright, and the phase somewhat is still alright. Then if you were to further go into the negative one, becomes unstable, then it is indeed really unstable, going to spike all the way up, alright, and then your phase is all changing, alright, as you can see your phase for your S first is somewhat okay, still stable, but after that you'll just go haywire. Alright, and this is just a lookout, and also in the point of view that how do you know that this Nyquist plot will move a long time? Alright, how do we measure? And therefore this measurement, we will always talk about our robustness measurement using the gain margin and phase margin, vector margin also, and your Doyle's stability criterion to an extent, alright, to determine the relative distance between two Nyquist plot in different time, right, meaning this one and this one, we are measuring their differences between against 1 plus CP, alright, 1 plus CP, alright, this is -1 point over here, alright, your plot, and this is -1, okay, and this is just measuring, alright, this is the Doyle stability criterion, alright. So in the next video we will talk about more on the plant, alright, instead of the controller anymore. So controller itself, we are just trying to ensure that the controller can be able to tahan the plant for a certain time period, alright, and we are measuring all this using what we have said earlier. Now we're gonna slightly talk about the plant and see what are the little variations that we have that can be explained in the plant. I shall see you there.